Welcome to the Bug Bash podcast, where we talk about all things software correctness and reliability. I'm your host, David Wynn. When is a bug not really a bug? In this episode, I talk with SRE veteran Dan Slimmon about a radical idea. Chasing perfect code may not be the best way to make your service reliable. Dan argues that once your code is good enough, most outages aren't caused by code defects. They're caused by weird interactions between different parts of your system, or by users doing things you would never expect. He shares wild stories from his career, including how a tiny database hiccup created a massive repeating traffic jam, and how a single user crashed servers by uploading a 3.2 gigabyte config file. This conversation will make you rethink what you thought you knew about bugs, quality, and what reliability truly means. Stay tuned. Hello, everyone. My name is David Wynn, your host of the Bug Bash podcast, where we talk about all things correctness and reliability. Today, we have on Dan. Dan, would you please introduce yourself to everyone?
I would love to introduce myself. I'm Dan Slimmon. I am an SRE of about 20 years SREing since it was called system administration. And, I've worked at a bunch of companies from tiny little startups to, HashiCorp size, Etsy size companies. And I've seen it all. I'm very interested in incident response, but I'm also very interested in preventing incidents before they happen by really understanding the behavior of a system in production.
Absolutely. And you also spoke recently at DC Systems Distributed talking about queuing theory.
I love queuing theory.
Yeah, all the fun stuff that comes along with that, because queues we won't rehash the talk here. People should go check it out on YouTube. But queues are everywhere, even if they are zero length, right?
That's right. Yeah. I mean, once you start, I got a textbook on queuing theory, and I learned, because I have a math degree. I worked through it with pencil and paper, and after that I was like, wow, these systems, like queuing systems, are everywhere, and everything I work, every distributed system is just a bunch of queuing systems in a trench coat. And understanding even just a little bit about queues gets you so far in terms of understanding system behavior. Often you don't even have to read the code. Somebody can just tell you, hey, look at this graph, and you can be like, I see what's going on there. So yeah, love queues.
Yeah, so check out that talk if you're interested in queues, but that's not what we're here to talk about today. Because today, I heard through the grapevine as part of that you had some interesting opinions about code quality and reliability, and how code quality does not always directly lead to more reliability. And I was hoping we could have a chat about that today. So I'll leave you there and say, could you expand on that for me, Dan?
Yeah, so code quality is important. Don't get me wrong. If the code is wrong, you can't have a reliable product, right? But very often, most people are never satisfied with their code quality. It seems to most software developers that you can always do better at code quality, and if you're putting the time in to do that, then it matters. What matters to the reliability of your product is that the software is correct. My position as a sysadmin / SRE is that for a given company, for a given reliability goal, software quality gets to a certain point. You have a certain amount of test coverage that you use to make sure that your software is correct, and then past that, it matters much less than other things that are going on in your system. So I guess what I would say is, most of the problem, once you've reached a certain level of code quality, most of your problems are going to be related to things that are not how good or bad your code is.
Okay. So what's an example of what you mean by the problems that are beyond code quality?
Right. So for example, at a recent job, I was working for a company where we had a standard stack where there's a web client and an API and a database. And what happened was it got slow. The application would get slow for like 30 seconds, and then it would get fast again for 60 seconds, and then it would get slow again. And it was just in this cycle over and over and over again. And and of course, the first thing you do is you check, well, did we do a deploy? The issue did start suddenly. And so we thought, well, did we do a deploy then? Did we do an infrastructure deploy then? What happened there? Nothing. We didn't change anything. The traffic pattern didn't change. It's not like we got a whole bunch of traffic all at once. And so we were just kind of stumped for a while. And what it came to find out, the database got wedged for like a few hundred milliseconds for some reason. I don't remember why. And during that few hundred milliseconds, a bunch of API requests were stalled. And then when the database got unwedged, they all returned all at once. So then the web client, which was refreshing essentially its API request on every 60 seconds, 60 seconds later, all those requests, all those clients that had been sitting there while the database was wedged, all requested at the exact same time, which resulted in a traffic spike, which wedged the database again for a little bit longer. Again, got into a cycle there where every time these requests all came in at once, they wedged the database for a little bit longer. Things got slower for a little bit longer, and the clients kind of grouped up with each other. So I ask you, what's the bug? What's the bug here, right? The code is fine. The code was working before the issue started. You could make the case that like the front end code shouldn't re-request after exactly the same interval every time. There should be some sort of jitter, and that's what we did to fix it. Was we added a little bit of jitter on the refresh intervals. But here's my thing: until this problem occurred, until this specific feedback loop happened that we responded to, there was no bug. If I had filed a PR, been like, we need to add jitter to this refresh interval because there's a potential that we could get into a feedback loop where we go around and around and things get slow, people would have looked at me like I was crazy. I would have been laughed out of the room because that wasn't a real thing, right? It's only a bug to the extent that it causes it interacts with the customer traffic in a way to cause a problem. So that's an example of a failure that has no particular bug associated with it. And I see these all over the place. They're very common.
Okay, so I feel like I have to quibble here just a little bit because, all right, I understand that in the framing here, bug seems like a code level issue as you're defining it. Is that right? What does a bug look like? When you use the term bug, I struggle to think that this does and does not exist at the same time because we shipped an artifact that has a property, that has this behavior that it displays. We just find out later that we don't like it. To me, that would suggest it was always there, it was latent, but I'm hearing you describe bug as like a smaller thing. Walk me through what you're thinking of here as a bug.
I certainly wouldn't say that a bug is necessarily a smaller thing than that. You have a bunch of pieces of software hooked together, and there's code, there's infrastructure code, there's software code, and there's a bunch of different pieces of infrastructure and software code that define different components that interact with each other. And each of those pieces, each of those components can be correct in the sense that it behaves as the writer expects it to behave in all situations. And yet, when you hook them all together and apply real-world phenomena to them, suddenly you have a problem in certain circumstances. The existence of a potential problem does not imply the existence of a bug. And once you have a real problem, only then does it become does it be do people decide, oh, this is because of bug X or bug Y or bug Z, and that's when the bugs, in a very real sense, that's when the bugs come into existence, is when we decide that they're bugs.
Do you think that there is a way to sort of rejoin these ideas together? Because this flipping thing is really annoying. Like, I'm really struggling with getting my head around that. And one attempt that my brain is trying to rationalize this with is there is a higher level property we're actually shooting for. We're trying to not foot gun ourselves. That was always what we expected. We just didn't see that we had lined everything up and we're pointing and getting ready to pull the trigger at a given, right up until the right circumstances aligned. But to me, that feels like we didn't do something right if we're sitting there pointed at our foot,
Sure. It feels and it feels that way because we have the I think it's a very common impression that is shared across software workers, that if a thing doesn't work correctly, then it wasn't built correctly. It wasn't put together correctly. And conversely, if it was put together correctly, then it would have worked. And I take a large issue with that whole concept. So another example would be illustrative here, perhaps. This is a little different, but suppose you've got a product and it's working great, and all the software works fine, and everybody's very happy with it. It all works correctly. It's very well tested, and you look at it and it's just working great. Okay, so then suddenly you start to notice there's out of memory problems happening, out of memory crashes happening on so you got an API server and there's out of memory crashes happening on it. And this is a real thing that happened to me in my memory. So I was investigating these out of memory issues, and it was really tricky because it's out of memory, so you crash before you get a chance to log anything, and our logs weren't good anyway. So the APMs, the Datadog APM spans were all sampled away, and I couldn't get. It took me like a week to figure out what was going on. But when I got to the bottom of it, it turns out that there's this one API client, this one user agent that keeps uploading configuration files that are like 3.2 gigabyte configuration files.
Every config file I've ever written, if it's not at least a gig, I'm not doing it right.
Yeah. Go big or go home, right?
Exactly.
They were putting entire jar files. I got the file, I decrypted it and checked it out. They're putting entire jar files in the config file, and they were the keys of a hash. Our software would have caught it if they were the values in the hash, but they were using the entire base 64 representation of a jar file as a key to a YAML hash. Why? Who knows, right? But what's worse is that when they uploaded the config files, it was fine. They could upload them just fine. But then some random number of days or weeks later, somebody would go to download the config file, and then we would run out of memory then. So again, what's the bug, right? Until somebody started submitting these crazy configuration files for reasons we don't understand, there was no bug. And whatever the fix was, we actually never ended up fixing this when I was working there, because the fix was too complex to do. We already had an API that said, well, you can upload. It had no explicit rule on how large a file you could upload, so we couldn't change that. And the customer didn't seem to care that their requests were returning 500 because it was just an API client that would retry, or they didn't care about it. I don't know. Anyway, we had a lot on our plate. We never fixed it. But even if we did have a fix, say we had some cool, crazy 1,500 line fix that would prevent these files from causing it out of memory or prevent them from getting uploaded in the first place. If somebody had gone and said, "Hey, I have a fix for this bug. I found this bug where if somebody uploads a config file with a giant jar file in the key of a hash, then our system will run out of memory, and I have a fix for that. And here's my fix. It's 1,500 lines. So just go ahead and merge this." The rest of the team would have been like, "What are you talking about? Nobody's doing that. Nobody's going to do that. That's sure, maybe that's a potential failure mode, but why are you focusing on this rather than all these real bugs happening today that you could be fixing instead of this thing that you've imagined might happen someday?" And so it's only after the user starts doing this thing to us that we decide, "Oh, there must be a bug because there was a failure here. Let's go fix that bug." And then maybe we fix the bug, or maybe we don't. But I really believe that until that happens, there's no bug to fix.
How do you square this with, I think it's Hiram's law, where to paraphrase badly someone much smarter than myself, all behavior of a system will become someone's dependency, whether documented or not. And a great example actually is now the 3.5 config file of a base 64 jar just like thrown in a YAML file. That's going to be my new example. But the one that I always think of for this is there's an Emacs user on a forum, and they found that there was some loop that it gets caught in with some function, and it caused the CPU to overheat. And so they pushed a fix, new version, hooray. And this user starts complaining on the forum, "Hey, could you guys just feature flag this fix for me? Because I actually had implemented this thing that detects whether or not the CPU temperature rises. And that's actually a key part of me doing the workflow if I hold down this key to raise the CPU temperature. So could you just feature flag this for me and reverse it?" So it almost feels to me like we're trying to square the circle of the reality of sometimes people come to do stupid things that are capable in the system, and we get to choose whether or not they're a bug afterwards, especially if they don't rise to the level of prioritization to where it becomes needful for a fix, right? Maybe the 500s, with our multi-gig config files happen every once in a while, or even better, maybe they only happen every third time. And so then there's a reset or something, and the node gets kind of recycled, and then the problem goes away because we've reset enough things enough times, and we turned it off and on again, and life is happy. Is that a good, or how would you square that?
Ultimately, the reliability of your product is the extent to which your users perceive that when they go to use your thing, it works the way it worked last time. It just works the same way whenever they use it and does what they expect it to do. To me, if one user with a strange use case needs it to work in a buggy way, and it stops working in a buggy way, that doesn't impact the reliability of the product. But if you have designed your product in such a way that a dozen customers are relying on a bug, then fixing that bug could very well cause a reliability issue. And so in that case, you have a bug, right, in quotes, where until it is fixed, it is not a bug. It's only a bug that you fixed the bug.
Gotcha. So you're almost describing reliability as a shared expectation between customers and providers. Is that right?
Yeah, absolutely. For example, it's not it's certainly not a number. Reliability is certainly not like how up you are or how much time your website spends up. And we know that because, an accounting app with 99.9% uptime could be a very reliable accounting app, because if it's down, people just go get a sandwich and come back and do their accounting after they come back with their sandwich. Whereas a database with a 99.9% uptime would be a piece of shit nobody would ever use. So reliability is completely about how customers perceive the usefulness of the tool, whether it does what they expect when they're trying to do things.
How do you capture that? So having worn the SRE hat for years and years and years, how do you put customer expectations on your reliability dashboard?
Not everything could go on a dashboard, man. I
The
I would
metaphorical
say,
dashboard, the one that we all live with in our hearts.
yeah, yeah. I prefer to what I prefer to do is, if a given concrete occurrence happens, a given concrete outage happens, and then I can usually figure out, what was the impact of that, and therefore what effect did it have on the reliability of our product. I try not to attach a number to that, because reliability is not a number, like I said, right? But there's outages that impact your reliability. There's outages that don't impact your reliability, and then there's a there's a there's not really a line to me between um, system behaviors that happen to cause an outage and impact the reliability, and system behaviors that carry risk of impacting customer facing reliability, but haven't yet. The reliability of to the extent that, like, a system is if a system is going to be reliable, then not only do you need to eliminate the problems that happen to cause concrete outages, but you need to uh, understand the behavior of the system well enough to infer which behaviors it has that are going to cause, or that have a carry a risk of a customer facing problem that haven't yet crossed your desk as an outage.
I'm not sure I'm on board yet, but I'm going to circle back around to that, because there's another question that popped in my
David,
head.
many people are not on board with these ideas. Oh, but that doesn't mean they're not right.
Okay. No, I appreciate that. And hey, we're here to have the discussion for sure. I want to take this back a little bit to where we started with the code quality component, because you mentioned sort of above a certain threshold that it becomes a little bit of a fool's errand in your mind to go chase. How do you have a sense for what that line is?
It's pretty straightforward, because when I'm at a company and look at the last 10 incidents that they had, or near incidents, if they happen to be tracking their near incidents as well, and I can just say, well, only 2 of these were actually caused by code bugs that we then fixed as code bugs afterward. Or I can say 9 out of 10 of them were solved, but were fixed by fixing code. That gives you a good sense of where the reliability issues are coming from. Like, once your code is predictable, has predictable behaviors to a certain predictable to a certain level, you don't suddenly stop having outages. Your outages just come from other places, like the ones that I just described, the examples that I described earlier. And at that point, like, you're probably doing pretty much what you need to do to make sure that your code is correct. And if you're missing something, you're missing something other than code quality. You're missing situational awareness, or risk awareness, or human-based safety systems, where people are. I watched a talk by Will, the CEO of
Antithesis, great company.
Antithesis. Thank you. Yes, I watched a talk by him, which is great, which was about he talked a lot about airplanes, and how airplanes, when they have gotten more and more reliable over time. We've had less and less chance that if you step onto an airplane, it's going to crash and you're going to die. But we've also started flying more and more and more. So the number of fatal aircraft accidents and the number of people dying in aircraft accidents has stayed relatively stable over the decades. It is true that some of the actual increase in reliability of aircraft can be attributed to technical improvements to aircraft, the software that runs them, the hardware that they're made of. We fixed the NTSB investigated some number of issues, and they were like, "Oh, we need to fix this. We need to fix this. We need to fix that." However, um, I would argue, and I don't know enough about airplane safety to give you citations here, but I would argue that the greater part of the increase in reliability of air travel has been because of improved systems of interaction among humans that make sure that we are flying safely, that we're picking up on environmental risks and communicating them appropriately to each other, that we're doing double checks and triple checks of systems. We have checklists that two people have to go through, and they talk about any discrepancies of the checklist. And so the technical improvements to the airplane can only get us so far before to increase our reliability. We need to address the ways in which the people building and operating the airplanes are interacting with each other and whether that's safe. And I agree, the exact same thing holds for software. You can get it up to a certain point where it has no bugs, or as far as you can tell, no bugs. And if you want to increase your reliability past that point, you need to address the human interactions among the human components of the system and between humans and this technology, rather than simply improving the quality of the technology.
You're almost describing this in I'm picturing a graph in my head, and one view of this is when there is a system with nodes and edges and the like, and when one view of this is when faced with a problem, you look at the nodes and you say, these are the things that need improving. And what you're suggesting instead is that the edges, beyond a certain point, let's say they turn on and turn off and generally respond the way that both sides expect them to. Beyond that, it's really the edges that drive the increased improvement from there. How do you make that tractable in this mindset? Like what does that look like?
That's great. I love the nodes edges thing. I hadn't put it that way before, but I'm going to steal that. Yeah. So at most software companies that I've worked at, there are teams that are responsible for products, like or sections, components of the product. Like who's the guy? The law about how a company will produce products that mirror its organizational structure, Conway's law. So anyway, you have a team that's responsible for a component, another team that's responsible for a different component, another team that's responsible for a different component. And my role, the role that I take on at most of the companies I work at, is I'll instead find an issue with the behavior of the overall system. When it gets this input, it breaks in this way. Or when traffic increases to this amount, it gets this much slower. Without regard for which node the bug is located in, I will follow and bring people with me as I do this, but I'll follow the issue itself as it runs down the edges between all the different components. Often product teams are not equipped to do this or not empowered to do this because their job is to build features within their node. And so I believe every software organization, especially the particular one that runs a software as a service product, needs to have some capability, whether it be a person or a team or a culture, an element of culture that enables people to chase behaviors or phenomena or problems across system boundaries without regard for who owns which system, and just chase them as they spider out through the box diagram of the system. That's what's missing from a lot of companies, and that's really what you need if you want to get your reliability to a certain point past the 100% code quality goal.
Some of the examples that you gave, and perhaps this is because of the shared view of reliability here, where there is a stakeholder in the room we cannot get requirements from very reliably. But it almost strikes me as sort of a specification problem, because we can encode a level of specification in the bits and bytes of the code artifacts that we build and run, but there is really a level of behavior that we're specifying either explicitly or implicitly over time at a higher level that sometimes comes into conflict with dynamics in reality or what have you. Do you think that there is a specification system or approach or framework that would help unify some of those things so that we could drive sort of overall health of the entire system?
Perhaps. I think so this is a great question. There's two distinct classes of entity that we're talking about here. So we have software, we have components that are built of software, and the software can be, you can specify, we know how to specify how we expect software to behave in the presence of certain inputs. You get these put these inputs in, you get these outputs. That I feel like solved is a strong word, but we get that. And
yeah, sure.
Right. And you can even specify what you expect the behavior of software components to be, or components of the system to be when they're connected in a certain way. You can say, if I send a message to this, it should go here, and then it should come over here, and then it should come back here. You can at least specify the happy path, so to speak, and some of the negative things that could happen. You could expect it to break down in this way when XYZ input happens. But software production is not an artifact. It's not a piece of code or the sum of a bunch of pieces of code together that can be specified in their entirety. It is a process that happens from instant to instant, and from instant to instant there are infinitely many things happening in the system that no particular person understands or cares about, and that reach far into the dependencies of the software that nobody at your company wrote, and even into the brains of your users who are deciding what to do, from moment to moment based on what your software, the responses your software. So it includes psychology, it includes law, it includes all these sorts of big human systems. It's a socio-technical system that includes all these sorts of big human ideas, and it's a process that unfolds from moment to moment. To specify what you expect your system to do in all cases, I think is impossible unless the set of cases that your software is designed to, your product is designed to respond to, is an extremely small set of cases.
But surely there are some, perhaps they are only negative ones, right? That we could say, again, like, we should not build a foot gun accidentally, or there should not be a situation where we line ourselves up to fail and we can see it as sort of a routine basis. Is that not a definable thing that we can explore at that level and somehow connect the dots?
You can absolutely do something like that, and you can get to a certain place by doing that, by thinking, okay, what are our expectations? You could work extra hard, work 10 times as hard, and come up with twice as many uh, expected situations that you can document and test for, and make sure that things are not going to fail in an unexpected way in those situations. I think that there's a hard limit to how far you can get with that. There will always be processes that can happen that you won't predict in advance, or you may predict them in advance but decide they're too unlikely, or there are a million different ways that a user could create a config file that has some crazy properties, right? But you only really care about the ones that actually happen in the real world. You won't know which ones are going to happen until they happen, which is why situational awareness of what your customers are doing and how your software is responding to it is can never be removed from the picture.
I remember reading an article that was clearly trying to be supportive, and it was along the lines of, there are only 4 billion floats. Why don't we just test them all? Which does, you can see where it's coming from, right up until you have 2 floats, and then you have 8 billion, or some, the combinatorics between the two, and you're like, I don't think this goes as far as I would like it to. Man, it's almost as if, because prediction, as you mentioned, does become a hard thing to do, right? As you get a huge amount of things that your system could do or could accept. I mean, look, if you wrote varchar somewhere in that database, you're going to have a fun time trying to explore everything that it could possibly accept, right? It helps to have a little help with the tooling, can help us get there. We can help alleviate the burdens. I say this because that's a thing that we see a lot of customers struggle with and we help with over at Antithesis. But it's really interesting to me how the users are sharing the definition of reliability. And what's funny is that I'm struggling with it because I'm starting to wrap my head around it. And I think about it in terms of things like if my mom was using this accounting app that you alluded to earlier, what do I think would differ between her expectations and what the team was writing to spec? Where does this break down? And I want to say next, who is right? Because that's the part that my brain wants to get to, but I get the sense that that's not important, right? It's more about, or do you think that is the right question that we should go after? I don't know. What do you think, Dan?
I think we have idealism and materialism. We have the idea that we can like buy from first principles, make a thing that works a certain way because we know what's right. We know what behaviors we expect of it and what it should do, and that the thing is either right according to our principles or it's not right. And if it's not right, then we just change it until it fits our principles. What we need in software as a service, I think, is more materialism. You have the concrete actions that your users are performing and want to perform from moment to moment, and you have their responses to those things. And by studying concrete cases where things have gone wrong, or things have behaved in an unexpected way to your users, right, or on an unexpected way to your developers, you may not end up with a helpful rule about how to make better software in the future and not have this class of problem anymore. But you'll fix a problem. You'll fix a thing, a concrete thing that's going on with your system, and then your system will be more reliable because regardless of whether the user should have wanted to have that behavior or not, they're now, it's doing what they expect it to do because you fixed a concrete problem.
Perhaps more than materialism, we might call it empiricism, right? It's about observationalness and driving that one forward.
Sure. I would say empiricism. It's not you need a mix, right? Because empiricism is, I think, the idea that like anything you want to learn about the world, you can learn by doing an experiment and observing the results of that experiment in the world. You learn about the world by interacting with it physically. That is true, but you also need to have, the reason your software exists is to perform a certain abstract function for people, and so you can't tell whether the system is materially doing the right thing or the wrong thing unless you have a well-developed, idea of how it's supposed to work and how it's supposed to represent things that occur in the real world. So it needs to bounce back and forth between empiricism and idealism. And if you go too far in one direction or the other, then you have a real problem on your hands.
That opens up a whole other can of worms that we don't have time for today because, unfortunately, Dan, I believe we are coming to the end of the time that we have. So what I wanted to say is thank you so much for the discussion. We're having we're here to hear interesting views, and I appreciate you sharing yours with us today.
Yeah, it's been a great time. Thanks for listening to me pontificate a little bit about this stuff, and I hope if you grapple with some of these ideas that you come back and tell me, actually, no, Dan, and maybe have me on the podcast again, and you can just you can argue with me about more of these ideas. I love to do that.
Yeah, if I'm going to have to take out some pencil and do math, that's going to be a while, I'm afraid. All right. Well, thanks, Dan. And to everyone listening, thank you for listening. Have a good one, and we'll see you next time. Thanks for checking out the Bug Bash podcast. If you want to reach out, maybe with an idea for the show, or maybe you want to be on it, send us an email at bugbash@antithesis.com. Or if chat's more your style, head over to antithesis.com and scroll to the bottom, where you'll find the link to our Discord. Until next time.